Modern AI integration is a mess. Command line tools, Node.js applications, and Python SDKs are all firing data streams into upstream APIs at once. The standard approach to securing these requests is writing application-level guardrails. You wrap every single SDK call in custom security code. That method breaks the moment you use a closed-source binary, a native IDE, or a third-party tool where you cannot modify the underlying code. The alternative is llm-fw. It is a local firewall that drops a network layer choke point directly at the operating system boundary. This architecture uses a tiered machine learning pipeline to monitor traffic without modifying a single line of application code. Shifting the security boundary to the network layer allows the stack to intercept traffic from tools that would otherwise bypass application-level monitoring. This requires a dual-mode interception strategy. Cooperative tools can use a standard HTTPS proxy, while everything else gets forced into an OS sinkhole. Node.js applications and native SDKs routinely ignore standard proxy environment variables. They hardcode their HTTP clients, which means they bypassed cooperative security. We edit the OS host file to intercept domains like api.anthropic.com, redirecting them to the 127.0.0.1 loopback address. Next, using OS-UML redirects, traffic aiming for port 443 is shunted to the proxy's port, 8443. Intercepting TLS traffic at this stage creates a cryptographic roadblock. Because the proxy is not the actual upstream API, the client throws a certificate error and drops the connection. To solve this, llm-fw plants a local root certificate authority directly into the operating system's trust store. When a tool tries to connect, the proxy uses this root CA to generate and sign a leaf certificate for that specific domain on the fly. This satisfies the client's security checks. The proxy decrypts the traffic, inspects the raw payload, and then seals it inside a new cryptographic shell to forward to the real LLM provider. This sequence enables payload inspection for uncooperative binaries, while keeping the TLS trust chains intact. Because the firewall sits in the critical path of every request, the detection pipeline must process streaming payloads without introducing lag that disrupts the user's workflow. Stage 1 of the pipeline uses deterministic heuristics and evasion normalizers as a high-speed first filter. Attackers hide their instructions to evade keyword scanners. They use base64 encoding, hex, or leet-speak to mask the text. The normalizer decodes these ciphers back to plaintext. Once decoded, O of 1 latency regex rules score the true intent of the request. This catches direct system overrides and simulated authority hijacks, like commands claiming developer mode is active. Stage 1 operates in under 1 millisecond. It neutralizes high-volume attacks, saving expensive machine learning computation for complex threats. A more sophisticated attack vector is the multilingual bypass. An attacker translates a known prompt injection into a foreign language to slip past English-centric heuristic rules. Writing deterministic regex rules across 100 different languages is an unscalable architectural task. Stage 2 of the pipeline uses the multilingual E5 small model to map text into a 3D vector space. These glowing nodes represent English intent anchors. When a malicious Urdu override arrives, it maps to the exact same semantic neighborhood. This cross-lingual alignment happens within the vector math. There is no translation layer required. We then have to constrain the false positive rate. The pipeline must distinguish between a malicious override being actively issued and one that is merely being quoted or documented. An intent versus mention gate identifies quoted blocks and downgrades them to warnings. This ensures the system maintains a ceiling on false positives. There is an edge case, the indirect injection. These are data-borne imperatives hidden inside tool outputs or document summaries. Because they are polite and indirect, they lack the aggressive language of a direct override, allowing them to evade the Stage 2 intent anchors. This JSON payload shows the exact API surface where this occurs. This is the data returned to the LLM via tool execution. To test the limits of semantic embeddings on these indirect attacks, we conducted a study using Bantu languages. This scatter plot graph tracks the cosine similarity data for out-of-table Bantu languages when analyzing planted tool result imperatives. The data points for malicious attacks and benign tool data overlap. There is zero clear separation. The embeddings fail to separate benign data from indirect attacks in these low-resource languages. This forces an architectural pivot, threat model isolation by payload surface. Instead of relying on a universal model, llm-fw applies dedicated surface-scoped action-verb heuristics exclusively to the tool_result block. Empirically, this surface-aware approach yields approximately 95% recall on indirect injections, while maintaining a 0% false positive rate. Treating all API surfaces as identical is a flawed premise. Isolating detection layers to specific payload structures is required to defeat out-of-distribution attacks. To prove the system generalizes to unknown threats, we measure performance against independent held-out datasets. This table details the benchmark metrics. On the safeguard dataset for direct injections, the system achieves an 84.9% recall rate, keeping false positives to 0.7%. For indirect injections, the surface isolation strategy proves out. The inject agent dataset shows a 95.2% recall rate with 0 false positives. Beyond machine learning accuracy, the system has to prove its reliability through in-process load testing. Deployments are gated by performance standards, requiring a 0% false positive ceiling and a sub-5,000 millisecond P99 latency under sustained concurrent load. By combining operating system network routing with tiered surface-isolated machine learning, LLM security is finally decoupled from application code.